This lecture is part of an online course on complex analysis and will be about Cauchy's integral formula. This shouldn't be confused with Cauchy's theorem that we covered in the previous lecture, which, although the two theorems are closely related, as we will see. So this says that if f is holomorphic in some region U, then we can write down a formula for f of w. It's just 1 over 2 pi I times the integral over c of fc over z minus w dz. So here, if your region U looks like this and w is a point here, then c has to go around once around w anti-clockwise. As I said, the convention in complex analysis is that whenever you go round things, you go round them in an anti-clockwise way. So it simplifies a little bit if we take w equal to 0, which gives us one less variable to think about, and then it just says f of 0 is 1 over 2 pi I times the integral of fc over z dz, where you integrate round 0. So the two forms are equivalent because you can just change variables, and this one is a little bit easier to remember. So in order to prove it, it's quite easy, just follows almost directly from Cauchy's integral formula. What we do is we write f of z is a constant plus a function g such that g vanishes at 0. So we're going to prove the special case with w equals 0. And so we just have to prove it when f is a constant and when f is a function vanishing at 0. So when f is a constant, we just have to show the integral over c of 1 over z dz is equal to 2 pi I. And this follows because by Cauchy's integral formula, you can just take c to be a circle of some radius r by deforming the contour c until it's a circle. And then, just as in the previous lecture, we can put z equals r e to the I theta, and our integral becomes the integral from 0 to 2 pi of r to the minus 1 e to the minus I theta. That's z to the minus 1, and then we get an r I e to the I theta d theta, and that's dz. And this integral, well, almost everything cancels out, and we get this integral is equal to 2 pi I. It's just 2 pi times this factor of I here. On the other hand, if g vanishes at 0, what we want to do is to show the integral around c of g of z dz over z is equal to 0. And what we do this time is we take c to be a circle of radius r. Again, we deform it to be a circle of radius r, where we're going to take r to be very small. And then we just estimate the size of this integral. So in absolute value, it's less than or equal to the length of c times the supremum of g of z over z on the circle c. And this is less than or equal to 2 pi r, that's the length of c, times epsilon over r, where epsilon is an upper bound for g. And this is equal to 2 pi epsilon, and now we notice that since g0 is 0, we can make epsilon as small as we like. So this tends to 0 as epsilon tends to 0, so this integral is 0. So you notice this is quite similar to the calculation we did in the previous lecture, where we showed an integral was 0 by taking a contour c and making it very big so that the integrand was small. Here we've sort of pushed in the opposite direction and made c a very small contour. So here we're just taking c to be a small circle around 0. So now we have a whole load of applications of Cauchy's integral formula. The first one is the following rather startling fact. Suppose we've got a contour c, and we're given a holomorphic function f on c, but not inside c. So all we know about f is its values on C, that then f is determined inside C. And that's because the Cauchy integral formula just says that f of w is equal to the integral over C of 1 over 2 pi I times f of z over z minus w dz. And you notice this only depends on the values of f on the contour C. So this is very strange because a holomorphic function to determine at this point here just by knowing its values around here, which is if you think about real analysis, this would be just ridiculous. It would be like saying I take a real, an open subset of the real line, and I specify the values of a function at the endpoints of this interval and ask, well, what are the values inside the interval? Well, obviously that's stupid. I mean, knowing the values of the function on the endpoints tells you very little about what it is inside, but even if it's differentiable or analytic or whatever. Incidentally, this is a special case of something we're going to show later, which is we don't even need to know that f on the whole of C. Even if we know f on a tiny little piece of the curve C, that's enough to determine it there. This is called analytic continuation, and we'll be discussing it later. So the next application is a sort of primitive form of the maximum modulus principle. So suppose f is defined on a disk U. Then, if we notice the value of f at w, if we take the absolute value of this, is at most the supremum of fz for z on this curve C. And that follows easily because f of w is just equal to 1 over 2 pi I times the integral of fc over z minus w dz. And this is less than or equal to 1 over 2 pi, sorry, in absolute value, I should put absolute value signs here, times, we want the length of the path, which is 2 pi r for some r, times the maximum value of f divided by z minus w, which is absolute value r. So this is less than or equal to the maximum value of f on the boundary. In fact, something much more general is true. First of all, we don't need to take the point inside the centre of this circle. It can be any point inside this region. And secondly, the path doesn't actually have to be a circle. It can be any path, and we find the a holomorphic function is bounded by the supremum of the values on the boundary. That more general version we'll probably show later. Next, we can figure out what the derivatives of f are. So, third application, we know f of w is equal to 1 over 2 pi I times the integral of fc over z minus w dz by Cauchy. And now what we're going to do is we're going to differentiate this with respect to w n times. So we get d to the n over dw to the n of f of w is equal to 1 over 2 pi I. And now we just differentiate this n times, and we get the integral over c of f of z over z minus w to the n plus 1, and then we get an n factorial in here. We should actually stop and check that this is really valid, because here we're differentiating under the integral sign, and you can't always differentiate under the integral sign. So we should check that this is possible. And it's possible because, first of all, C has finite length. And secondly, this integrand f of z over z minus w has a continuous derivative, or continuous derivatives, near the path C. And as long as these two conditions are satisfied, you can differentiate under the integral sign in real analysis, and pretty much the same thing works in complex analysis. So this is actually a valid differentiation. And there's one really striking consequence of this, which is that d to the n f over dw to the n exists. So all we assumed about f was that f was differentiable once. That's what holomorphic means. and this automatically implies it's differentiable any number of times. So, as I remarked a couple of times in earlier lectures, there's absolutely no reason why this should be true for functions of a real variable. There are lots of real valued functions that are differentiable once but not differentiable twice, and so on. By the way, I should explain that this means differentiable once in an open region. Because to be holomorphic, it has to be holomorphic in an open region. You can have complex functions that are differentiable once at a point, but not differentiable any number of times. The proof of this requires, doing integration in an open region or something like that. So it's definitely not true just at points. So next we have Liouville's theorem, which says that if f is bounded and holomorphic in C, then f is constant. This is a really useful theorem that we're going to be using lots of times later on. And you may think there's an obvious counterexample. So what about sine of x? Well, sine of x is bounded and it's certainly holomorphic, so isn't this a counterexample? Well, no, this is not bounded on the whole of the complex numbers. I mean, you sort of think sine of x is bounded because you're used to it being bounded for reals. Now, just to remind you, when x is on the imaginary axis, we saw that sine of x actually gets really, really big. So anyway, this is a rather striking theorem because it obviously just totally fails for well-behaved functions of real variables. There's absolutely no reason why bounded real functions should be constant. So how do we prove Liouville's theorem? Well, this follows easily from what we did earlier. We just look at the derivative of f of w, and this is 1 over 2 pi I times the integral of fc over z minus w all squared dz, where we integrate round some curve c. And now we're going to take curves, the path c to be a circle of large radius r. I tend to use capital R for large radii and small r for little radii. And then the absolute value of the derivative is going to be at most, well, it'll have a 1 over 2 pi I, and then we have the length of the curve c, which is 2 pi r, and then we have the supremum of f, and then we want to divide it by z minus w squared, which is going to be r squared. So this is going to be less than or equal to the supremum of f over r. And since f is bounded, this is constant, so this tends to 0 as r tends to infinity. So the derivative of f is equal to 0 at all w. So this implies f is constant. And I've been told to make more exercises in my lecture, so here's an exercise. Suppose that the function f has absolute value that's bounded by some polynomial in C, polynomial in x and y. Then show that f is a polynomial, assuming it's holomorphic, of course. And the proof is quite similar to this, except you have to look at a high derivative of f there. Next, another very astonishing application is any holomorphic function can be expanded as a power series. And to see this, what we do is we expand 1 over z minus w as 1 over z plus w over z squared plus w squared over z cubed, and so on. And I'm going to ignore all problems about convergence for a few minutes and then come back to them later. So if we ignore convergence problems, then we just write f of w is this, times the integral of f of z over z minus w dz. And I might be able to set this as equal to the sum over n of 1 over 2 pi I times the integral over c of f of z over z to the n plus 1 dz w to the n. And let me put a big red ring around this equal sign to remind us that this is not at all clear. Here we're changing an integral and a sum, and you have to be a little bit careful when you're doing that. Anyway, this is equal to a sum over all n of 1 over n factorial times the nth derivative of f at 0 times w to the n. So this just means nth derivative. And this, you'll notice, is just the Taylor series expansion of f, assuming the Taylor series expansion converges. So we've shown that f is always equal to the Taylor series, provided this equality sign here is okay. Well, to check this equality sign, what we have to do is to sort of check the tail end of the difference between these two expressions. And what this comes down to is showing that the integral over c of f of z times w to the n over z to the n plus 1 plus w to the n plus 2 over z to the n plus 2 and so on dz tends to 0 as n tends to infinity. So this is the sort of difference between the first n terms of this and this expression here. And this is easy provided it's okay if the absolute value of w is less than the absolute value of z, because you see, if the absolute value of w is less than the absolute value of z, then we've got a sort of geometric series here that converges very nicely, and we've got a w over z to the n sitting in front, so that's going to tend to 0 as long as n tends to infinity. So this is valid. So this Taylor series expansion is valid if f is holomorphic for z less than r, where r is some number bigger than w. So for real functions, of course, this just fails totally. So the classical example of this is e to the minus 1 over x squared. So it sort of looks a bit like this. And all derivatives are 0 at the origin. So the Taylor series converges, but it doesn't converge to this function at all, even though this function is infinitely differentiable. So for complex variables, if it's differentiable once, then the Taylor series converges to the function. For real variables, it can be differentiable any number of times, and that really says very, very little about the Taylor series. I'd say conversely, if a Taylor series converges for z less than r, it converges to a holomorphic function. I won't prove this quite now because I was planning to do convergence of series of holomorphic functions in a few lectures' time, and it will be just easier to do all that in one place. By the way, I just better make a few comments about convergence of Taylor series. So suppose we've got a Taylor series, say a0 plus a1z plus a2z squared and so on. And suppose it converges for some value z0. Then in particular, aiz to, I better not use I, anz to the n is bounded. Because a convergent series, its terms must be bounded. And this implies a naught plus, anz naught to the n plus a1z plus a2z squared and so on converges if z is less than the absolute value of z0, because this you can then check that this converges faster than a geometric series corresponding with the terms having ratio z over z0. So what we see is that if we've got a Taylor series around 0, then there's some number r. So r might be 0 or it might be plus infinity, such that the series converges if z has absolute value less than r. It might not converge anywhere if r is 0, and it diverges if z has absolute value greater than r. So if r is plus infinity, it doesn't diverge anywhere. So Taylor series in complex analysis always converge in a circle, or rather a disk. By the way, in case you're wondering what happens if the absolute value of z is exactly equal to r, the answer is it gets really complicated. Sometimes it converges nowhere, sometimes it converges everywhere on the boundary circle, and sometimes it converges somewhere and doesn't converge elsewhere. In fact, this is essentially the very tricky problem of asking when a Fourier series converges. As the final example, I will discuss Morera's theorem. This is a sort of converse to Cauchy's theorem. So Cauchy's theorem says that holomorphic implies the integral over c of f of z dz is equal to 0 whenever c is a closed curve such that f is holomorphic inside it. So Morera's theorem says that if the integral of c of fz equals 0 dz equals 0 for all closed curves c contained in U, where I'm going to U should be simply connected, I guess. This implies f is holomorphic. And the proof is very short. We define big F of z to be the integral from a to z of f of z dz. So we've got this region here. We're fixing a point A, and we're just integrating to a point z and using that to define f. And notice this is well defined. And the reason it's well defined is because of our assumption that the integral over any closed curve is equal to 0, because if we tried integrating along a different path, we would get the same answer because integrating around the whole of this curve gives 0. So this is well defined, and once you've shown that this is well defined, we can just check that f has derivative little f. So this is a very easy calculation which we more or less did when we were showing that functions had an antiderivative, for example. So we just check that once we've defined it like that, it has derivative f. Well, since it's got a complex derivative, this implies f is holomorphic. And we just saw that if a function is holomorphic, its derivative is also holomorphic. So our function little f is holomorphic. We're going to use this later on when we discuss convergence of holomorphic functions. So this will be a useful result to show that under mild conditions, a limit of holomorphic functions is also holomorphic. So there's one very important application of Cauchy's integral formula, which is analytic continuation, but this is so important I'm going to make the whole of the next lecture about it.